Welcome to this presentation on deriving the equations of motion for a multi-degree of freedom system. Today we'll analyze a mechanical system consisting of three masses connected by springs as shown in the figure. Our goal is to derive the equations of motion for each mass and represent them in matrix form. Let's begin by understanding the system setup. Here we have a system with three masses, a top mass m, a middle mass 2m, and a bottom mass m. These masses are interconnected by springs with stiffness values K, 2K, and 3K, and some springs are anchored to fixed points. The top mass is connected to a fixed point by a spring K, and to the middle and bottom masses by springs K and 3K respectively. The middle mass is anchored by a spring 2K and connected to the bottom mass by another spring K. The bottom mass is fixed to the ground by a spring K and interacts with the other masses via springs 3K and K. So let's start with the top mass M. For each mass, we will apply Newton's second law, force is equals to mass times acceleration, where the forces are due to the springs. Now, the forces acting on the top mass M include: one, a restoring force from the spring K attached to the fixed point, a coupling force from the spring K connecting to the middle mass, and a coupling force from the spring connecting it to the bottom mass. Now, applying Newton's second law, we then get mass times acceleration is equals to minus kx1 minus k into brackets x1 minus x2 minus 3k into brackets x1 minus x3. So if we simplify the equations and rearrange them, we end up with the bottom equation. Now let's analyze the middle mass 2m. So the forces acting on it are a restoring force from the spring 2k anchored to the fixed point. We have a coupling force from the spring k connected to the top mass, and finally a coupling force from the spring k connecting it to the bottom mass. So the equation of motion is that by applying Newton's second law, and then the only thing left to do is for us to simplify and rearrange the equation, and that is the result. Finally, let's examine the bottom mass M. The forces acting on it include the restoring force from the spring K attached to the fixed point. We have the coupling force from the spring 3K connecting it to the top mass, and finally a coupling force from the spring K connecting it to the middle mass. Applying Newton's second law, this is what we get, and we simplify and rearrange, and that is the result. So this completes a set of equations for all three masses. Now let's present these equations in compact matrix form, which is useful for further analysis like model analysis or numerical simulations. So the mass matrix is diagonal with masses M, 2m, and m. And the stiffness matrix captures the spring couplings and is symmetric. And that is the final answer.